Hello everyone, welcome back to the another lecture. So my name is Ashish and today we will see the PLECS demonstration of soft switching in the DAP converter. So in the last two classes you might have seen that we have discussed about the soft switching concept, how exactly the soft switching happen in any converter. Then we have started discussing about exactly how DAP converter experience the soft switching, when the soft switching happen in the DAP converter. Then we have discussed about the one ratio constant m, right? So for greater m greater than 1, in which particular bridge we will going to get the soft switching. For m less than 1, in which bridge we are going to get the soft switching. What are the reasons that the soft switching not happen when that m is greater than 1 or m is very less than 1? Okay, why at m is equals to 1 we have the really luxurious soft switching for basically both the bridges, and it will work perfectly fine. Okay, so all this thing we have discussed in the previous two videos. Okay, now I just wanted to show you that how exactly we can see, because in MATLAB it is not possible to see the losses across the device, right? If I wanted to see that what is my turn off loss or turn off loss in the MOSFET during the operation, that is not possible in the MATLAB. So there is another software like PLECS is there, and another is a LT Spice. So in those two software you can easily see what is the exact loss happening across the device during turn on as well as during turn off, or overall loss, right? Even conduction loss you can identify. So just I wanted to demonstrate you those concepts, those things from this video, and mostly will understand this. Okay, so if you have the PLECS software basically installed in your PC, then I will just quickly guide you how to make the model in the PLECS, and then we will try to understand few things. So what we are going to do in this video is a recap of the soft switching in the DAP converter that we you already know. So I think there is no need to discuss that thing. Then something about the PLECS software, how the things are there and all, how to use that software in very quick time. Then demonstration of the soft switching in the DAP converter, and next we will talk about the hardware prototype basics. Okay, so few of the user have asked me like, sir, if I wanted to make very small scale hardware prototype, then how I can proceed? Okay, so if I wanted to make a hardware, then what are the steps? So we will just try to intuitively try to discuss in 5 to 10 minutes that, okay, if you wanted to make very small hardware prototype, what things you need to keep in your mind and how you can proceed further. Okay, so with this I will start this lecture, so let's get started with this. So here I am in my PLECS model. If you know about the PLECS environment, then maybe I don't need to discuss this. But for those who don't know about the PLECS, so PLECS is just similar to the MATLAB. So mostly a thermal kind of simulation you can do in the PLECS, as well as if you wanted to analyze the losses and all, then you can use this software. Okay, so it is its interface is exactly similar to the MATLAB. Like how? So you just click it here, and what you want you can just type. So if you want MOSFET, so just write down the MOSFET. You will get the MOSFET with body diode, everything you are going to get. Okay. Now if I am taking it, okay, what is the difference? Right, so if I am going to take this, what is the difference? Because these thing we can take in MATLAB as well, right? So thing is you can basically add the thermal parameter here. So if you have the libraries, so I have one library available for me how to add that library. Maybe that part I'm skipping here. So I have those many of MOSFETs available. So these are our 1200 volt MOSFET. So a lot of MOSFETs are available. So I can select that particular MOSFET, then its actual thermal model parameter will come, and then if I will apply, then I can use that parameter. Okay, so this is how actually and if you wanted to add some parameter on state resistance, that can also you can add through the data sheet. Okay, so that is the advantage we have basically when we are going to do the simulation in the PLECS. So you can use actual model. Okay, so that is the advantage. Same thing we can do in a basically LT Spice simulation as well. So there also we can import the actual model and we can do the analysis. Okay, so now how I have constructed the circuit. So it is a similar kind of, so I have my DC source VDC, So how exactly we will going to get the DC source here? So just write it down simple, DC voltage source, so you are going to get the DC voltage source, so just like the MATLAB. So it is almost similar to the MATLAB. Okay, so you don't have to be worried that's how to use this software. Just try to download it and try to use it. Okay, maybe it requires the licensing. My college have licensing, so I can easily access it, but maybe you can download it and try to install it. Okay, if you wanted to learn the things in more detail. Okay, because doing the simulation is not only the objective, we need to analyze the things what is exactly happening. Okay, whether the things are visible actually or not if you go in a practical implementation, right? So all those things we need to consider. Now, so I have my DC supply voltage, so I am going to take the example of 800 volt input, 800 volt output, the same example we have discussed in open loop simulation as well as in closed loop simulation. Okay, so same example, same parameter I am going to take, and with this parameter we will see whether we are going to achieve something or not, whether output I am going to get or not. So all those things we are going to see. So I have my DC voltage source. Now the MOSFET. So MOSFET, I have added some on-state resistance. Okay, so 0.3 is my on-state resistance. Then thermal parameter. So I have used one MOSFET here to have the actual thermal modeling. Okay, with us. Okay, how to add this, that is another part. So you can I will maybe tell you if you need it. I will pin the procedure to add in comment section. Okay, so if you are actually working on it. Okay, so the four MOSFETs are there. Then I have my inductance. Okay, then one linear transformer. So again the parameter you need to specify leakage inductances. So this parameter we all anyway we will keep the 0. And what is my turns ratio? So I have told you that our turns ratio is 1, and then magnetic inductance is very high, and RF is basically infinite. Okay, then here only thing is to have measure the voltage you need to write it down the voltmeter. Okay, so that is the only thing difference. So you just like how actually in practical system we will implement, so same kind of system is here. So you need to add voltmeter, you need to add ammeter if you wanted to measure the current. Okay, so just only those two things are differ. So voltmeter, ammeter I am going to connect. Then again I wanted to see the voltage here, I wanted to see the voltage here. Then I have transformer. Then again my secondary bridge is there. Okay, and then my output capacitor. So again the same value which we have used previously. And then my load resistance. So for 30 kilowatt power we have done the simulation there. The same for 30 kilowatt I am going to do the simulation. Okay, so these are the very basic fundamental blocks I have added. Okay, now another thing, my discrete mean block and display block you already know. So here I am going to see my output voltage. Another thing is basically this particular block, if I wanted to comment, so just go to signal, go to block, and from block are there, so you can just tag them. Okay, now two more block I have added here. These are the heat sinks. So if you wanted to add the heat sink, so you can add the heat sinks. So what are those heat sinks? You know about for thermal management, because my MOSFET anyway going to heat up. Okay, if I will run the simulation continuously, these MOSFETs are anyway going to be heat up, right? So basically for that I have just calculate some value and put the heat sink for this MOSFET pad, and then I have keep some RTH value of 10, and I am assuming that my ambient temperature is 25 and it will increase with the simulation. But now as I am adding the heat sink, so it is not going to be make any difference. Okay, then basically again my pulse logic is same. So these two switches will turn on at the same time, and these two switches will turn on at the same time. Okay, and the operation of these two switches is 50%. Then basically this bridge is shifted by this bridge, right? So if that is called as the phase shifting between the two bridges. So if it has some basically pulse, then the pulses we are going to give here, these are phase shifted. So for that what we will use pulse delay block. So here I am generating the pulse, so it is a high state one, low state. So again it is a pulse generator. You just like the MATLAB, we will take one pulse generator block. Then high side, low side, switching frequency 100 kilohertz, and we know the duty cycle 50% we apply. So these pulses I am going to apply to S14. So what is my S14? So this is S14 and this is S14, right? And its NOT gate is given to the S23. So this is S23 as well as this is S23, right? Now the whatever pulses we are going to generate here, we need to phase shift them. So again the pulse delay block is there, so you can just use the pulse delay block, right? So pulse delay block is there, and using the pulse delay block, what is the duration you wanted to give. So you know that we have calculated in our script what is the time which we need to phase shift, what is the angle. So that 49 degrees is something angle we got, and that 49 degree corresponding to how much time, so that time we need to give it here. Okay, so that particular phase shift basically I am going to give here. Okay, and then basically it will generate the two signals. So S58, so S58 is this particular, and another the S58 is this one, right? Because these two switches will going to turn on at the same time, and another would not get it S68, so X67 is given to the these two switches. Okay, so it is just similar to what we do in the MATLAB, right? Now what additional feature we have here is basically a switch loss calculator. So basically you just type the switch loss calculator, so you can have the basically switch loss calculator. Now what we are going to get inside the switch loss calculator, so it will ask you the average and time, basically for what you need to calculate the losses. So I assume I am keeping it as 0.1. Now second thing, it will ask you basically what losses you wanted to calculate. So total loss, turn on loss, turn off loss, what losses you wanted to calculate. So conduction loss, and we need to specify across which device you want it. So what you will do, you will just keep this divide and just insert inside this. So if you will going to keep this, so now if I will use this particular block, so it will show me, let me, I am interested, suppose is in only turn on losses. So I have just keep this particular device here, and basically turn on losses I have added. So now if I wanted the another device, so I will just take this and I will add it here. So this is my another device you are going to see. Okay, then another third device I'm going to add, and one fourth device. So these are my four devices I added. So what it will give, it will give the a total of all the four MOSFETs. Okay, so these four MOSFETs are there from the input side, so it will calculate the turn on loss. If I will switch, if I will choose this conduction loss, so it will show this kind of. So these are 5 parameters, so I am going to use the display block. So if I will click only one parameter, that is turn on loss, so it will show only the turn on loss. If I will select all the parameters, so it will basically try to give the all the parameters. Okay, so now as of now I am going to see only the turn on loss. So this is my one basically loss calculator, switch loss. Now I will take another for the secondary bridges. So again I am going to tick it there, and I will just want the turn on losses here. Now what are the different MOSFET I need? So I will take the secondary side MOSFET. So this is the first MOSFET, then this is the second MOSFET, then this is the third MOSFET, and this is the fourth MOSFET. So all the four MOSFET I have taken here, and I just wanted to see the turn on loss. So okay, and then I will going to use a display block to see what are the numbers we are going to get here. Okay, so just connecting this. So it's a very easy platform to use, and mostly sometime I will use this because it will help me to analyze the few patterns. Uh, Also LT spices are really good because look, what is the drawback of this is, if I wanted to work on gate drives, okay, if I wanted to make my gate driver, then I cannot basically provide the generated gate signal like through some block. Now here I will use some when we do the control and all, that time also we need to add few things, right? We need to add use a pulse generator block or something. But if I wanted to make my own gate driver signal and I wanted to feed it here, get with respect to gate and source, that is not possible here, but that is possible in the LT spice. So that is the beauty of LT spice. So maybe in future we will try to understand about the LT spice as well, how exactly, because my work is mostly till now I have done is on some hard converters, hard switch converters, as well as soft switch converters on the gate driver. So when I will work on the gate driver, I mostly use the LT spice because there only I can simulate actually my circuits, and I will work on mostly charger part. So these are the few topics I am currently working on, and if you people wanted to, maybe most of my viewers are connected with me. I'm really happy that you people connect with me and ask me the question, and I'm really happy to help you people as well. So that's really a great experience for me. So okay, apart from this, let's continue the discussion. So switch loss calculator we have added. Now I will just run the simulation. Okay, so another blocks are, you already know, familiar, that this is a multiply block. I wanted to show the voltage and current multiplication, that is power. Okay, and this is a just a display block, and I'm just seeing the gate pulses here. Now I will just run the simulation. So I have set the parameter and this phase pulse delay block in such a way that I should get the 30 kilowatt power. Okay, so now there is one simulation block. You can just start from here. So once we started, you can observe the things. So it will slowly start. So you can see that basically the losses on the switch. So these are on the turn on losses. So you can see that the turn on losses, overall turn on losses in this particular switch is 0. Overall turn on losses here as well is 0, and overall basically these bridge losses are also 0. And you can see that this block corresponded to what, conduction loss. Then maybe this is what we can just see it here, what these parameters are. So first is for conduction loss. So basically overall conduction loss. So I have just taken 4 switches here. So this primary side switches. So conduction over loss basically 77. What is my another switching loss? So switching loss is there. Turn on loss, turn off loss. Now you will ask me, sir, switching loss corresponding to turn on and turn off, right? So yeah, you can see that turn on loss is 0, and the switching loss and turn off loss is basically actually the same numbers, right? So this is the thing we can observe. Now it is not possible here, I feel, to have the actual current flowing through the MOSFET, and what is the voltage across it. Just I will check once and I will come back. Yeah, it is not possible here to actually see the current flowing through the MOSFET and voltage across it. So that is possible in the LT spice. Okay, so there actually you can see that, okay, current falls to 0 before voltage turn on, or voltage falls 0 before current turn on, whatever happened. So here ZVS is happen, and what happened exactly in the ZVS you do. Okay, so that is not possible here, but that can be possible in the LT spice. So maybe I will show you someday LT spice simulation as well, how to model this. Okay, so I have this model available with me, so that's why I just wanted to quickly show you this. What we will do one more time is, I will just stopping the simulation. So you understood that, okay, turn on losses are 0, and basically here 800 volt input, 800 volt output, and turns ratio is 1. So anyway we know that this basically this is a case of m equal to what, m is equal to the 0. Okay, m is equal to 1. Now I will just try to change this block delay time with no delay, not delay time. I will try to change the input. So if I will change the input for 800 to basically 400 volt. Now you know that basically m value is going to be changed, and m value is influence the switching loss. Now we will see. Okay, I have just changed the input, keeping the output same. Whether I am going to get the output same or not, that is second thing, but I will just start the simulation to observe whether we are going to get the losses same or not. So you can observe that in one of the bridge losses still it is showing the losses equal to 0. So that means I am still in the what we can say basically 0 switching zone. Okay, 0 voltage switching zone. Now I need to change few more parameters, and then we can observe that okay, it is actually coming to the non-ZVS zone. So what I have done here, just a small modification to show you that exactly a turn off losses we can observe. So what I have done is this my voltage I have halved already. Again with that this phase angle I have just tried to change. So phase angle is now 0.1. Okay, because of this my 0.1 into the previous what is my phase shifting time. Okay, and when I am going to run this simulation, so you can observe that there is a losses happen in the switch. Now what is my m here total, you can find it out. Another thing is basically, okay, so my first bridge has still turn on losses as 0, but my second bridge has a turn off losses of what, my second bridge has a turn on losses of basically 27.26. so why this is happening? Because this particular side, secondary side, is now not having the ZVS shown. Why this is happening? Because we can observe the current wave shift. So I will just quickly show you the current wave shift one, whether what kind of current wave shift we have, and because of the wave shift only these kind of things are happening. So okay, so this is the nature, and we have observed that when such a kind of nature is there, so my output side bridge or second bridge having a non ZVS. Okay, so that's concept we have learned in the previous class, you understood. I have taken this scenario of such a waveform, and I have told you that at what instant what is required. So you I guess you remember the condition for the ZVS. Okay, turn on. So what is the direction of current, where IL is positive or negative for which particular switch to turn on. So during the on of which switch what is the direction of the current IL, so that determines whether the ZVS happen or not. Okay, and we have taken this example as well, and there we have discussed. Okay, so that why the secondary switch, secondary bridge has non ZVS. Okay, so those things we have already covered. So I guess this is for this particular video. We have seen so many things here. So I guess we have seen so many things here. So this is all for this particular video. We will quickly learn about how exactly we can make the hardware prototype. Just I will give you some intuitive guides to you, so that if you are starting, maybe I will make one separate video on how exactly step by step you can proceed with the hardware development. Okay, but I will just give you some intuitive guide as of now. But I hope so. So far, so now, whatever we have discussed, you understood, I guess, how basically Plex environment is. It is really user friendly. You can easily use it just like a MATLAB. And if you wanted to build something and observe something, you can easily do. Okay, so those who are working on the LLC converter or CLLC converter, they are mostly interested to see whether my ZVS happen, ZCS happen or not. So that time, basically this software is really important, because you can easily get the loss analysis, right? Whether my basically overall loss is happening zero or not. So there it will be really helpful. Okay, now I will just quickly move to the another window, and then we will intuitively discuss about the hardware prototyping. So here we are. Now we are just quickly discussing this part of the hardware prototyping basics. Now let us say you wanted to make 100-watt prototype. Okay, so what things you need to do first? So you know about the MATLAB. So you will just initially draw a MATLAB model. So you know how to calculate the, you just assume that as of now you are going to operate it in the open loop condition. Okay, as of now. So what, how you will going to proceed? So you know our input requirement, you know your output requirement, you know based on that you will calculate some load resistance value, right? And basically need to select the MOSFET. So let us say if you are operating at 100-volt input, 100-volt output, which MOSFET you are going to use? At least use the 200-volt MOSFET or 300-volt MOSFET. So how to select the MOSFET? So that is the another thing. So based on RDS on, okay, lower the RDS on, better the performance, losses will be less. Okay, so try to find it out. So there is a really interesting way to select the MOSFET. We actually make basically series of MOSFET comparison. We'll compare side by side, we calculate the actual losses for our actual hardware prototype, and this is, I will show you one day maybe that how exactly we'll make the overall file, and how exactly we compare the MOSFET. It is not like, it is not so simple that you will see, okay, I need a 200 300 watt MOSFET, I will just see, and whichever MOSFET. So from where you can basically buy this. So element 14 is the base side. This is what I feel, because there is no custom clearance or something which is required. So you can just order and it will come. Okay, based on the availability, you can order from element14.com. okay, so this is the website you can refer. So so what I am talking about, that selection of the MOSFET is again a really interesting thing. Not like if I want 200 300 volt MOSFET, I can easily take. So you need to see the lot of parameters, like what is this COSS, output capacitance, what is this charge, what is this Q requirement, what is the basically RDS on, how its RDS on is going to vary with respect to the temperature when I'm going to actually operate it into the my environment. Based on that, we will going to select the heat sinks and all. So all those things are there. But as of now, for just trying to make a prototype just for understanding purpose, what you will do, you will try to find out the MOSFET which is having lower RDS on, and try to buy the total 8 of the MOSFETs. Okay, now second thing is basically inductor design. So either you can buy, what people usually do in practice, if you have maybe gone through the some research paper, so you have observed that a few people basically include this L inside the transformer only. So having the transformer with having the highest value of magnetizing inductance, and basically if you short the secondary, you can find it out that what is the leakage of this transformer. So transformer leakage is used as the L. This is how actually people make. So I have seen most of the time people will not buy the transformer, they made it by themselves, and we have also made by ourselves. I will just show you. We have made the you can see, I feel this transformer, this is the not the transformer, this is the inductor. So we have actually made it by our hand, and I don't have right now, but we have actually make the transformer as well. Okay, so this is how actually for small prototyping you can make, and you can measure as well. Okay, then what other things are required? So this is the about the this particular part. So what is the actual part? So capacitance, you can place some sort of basically provision. Then what other things you can need is basically you need the gate driver. So try to get always isolated gate drivers, okay? And isolated gate drivers with how to select the gate driver, that is also really interesting thing. So try to get the gate driver which is having the highest peak amplitude, peak current, which can deliver the higher peak gate current value, okay? So this is the really fundamental and very important thing, okay? Whenever you select the gate driver, try to find it out what is the maximum peak gate current it can deliver, because anyway you are going to select the voltage source gate driver. So there are the voltage source gate driver as well as current source gate driver, but mostly we will go for voltage source gate driver, because a current source gate driver is a research area where I am also working kind of, but I will suggest that okay, don't consider as of now for current source gate driver. There is a really good difference and very interesting things about the voltage source gate driver as well as current source gate driver. Maybe I will make one video where we can discuss all those things, okay? But as of now, try to find out the voltage source gate driver which can deliver the maximum peak current, okay? And having the voltage of at least 500 volt for our 200 volt. So like for isolation purpose, 500 volt it is enough, more than enough, okay? So you can find it out that. So there are also whether to go for basically single channel MOSFET or dual channel MOSFET. So it is completely based on you, okay? But use isolated one, okay? Otherwise you need to add opto isolator again, and that is again basically a huge task, okay? So we don't want that. Then for the secondary side also we need that. Then we needed the voltage sensors, okay? So how to select the voltage sensors, I have made one very basic video that is available on my YouTube channel, but I wanted to explain those things as well. Like there are really good points when we are going to select the basically voltage sensors. So if you have the knowledge, you can select one voltage sensor. Then we need to whether we need to select whether we need here a current sensor or not, because we are if you are going for closed loop, then only you are going to need the voltage sensor as well as current sensor. So current sensor you can place it here, and you can measure the current as well, okay, if you are going for closed loop operation. But if you wanted to just go intuitively hardware development, then as of now you can just add the voltage control voltage basically for voltage sensing, and for current sensing you can keep the provision in the PCB. So making a PCB itself is again a really interesting area, basically how exactly you can utilize the space and all. So there are a lot of things to talk, but we have our constraint, and we have discussion which belongs to this video. And I guess we have talked I have talked so many things in this video, but I should not, because we should be restrict to our content. This is what more important, because you are here to listen what exactly is required, okay? So I feel this is for this particular video, if needed anything, I will surely discuss with you, okay? I'm really fine to discuss with you. If wanted to connect with me, you can connect with me on LinkedIn. There maybe if you have any doubt, I am happy to answer you, and if needed we can have the small teams meet or something, we can discuss over a teams call. And if it is in my range to answer, I'm definitely, and if I have the time, if I have free time, I'm ready to I'm really happy to help you. So that's it for this video. In the next class, what I'm thinking initially of to start with the extended phase shift modulation, like how exactly the extended phase shift modulation is basically going to be there, how it is differ from the single phase shift modulation, and then how to implement it, okay? So open loop simulation, I will just quickly show you open loop simulation. My interest is to show you how exactly we can do the closed loop simulation for extended phase shift, okay? So that part I wanted to cover, but before going to there, what I feel that most of you people have asked me about the small signal modeling. So I feel for you people, small signal modeling is really hot topic, okay? So what I was thinking, either to make, if I will get I will find the free time from my schedule, I will basically quickly make a notes of basically small signal modeling, and then we can discuss it, okay? Very quickly within 15-20 minutes video, I am going to discuss the small signal modeling as well of the DAP converter, okay? So see you then. Based on what I'll going to prepare, I will come up with the next lecture, okay? So thanks for watching this video, and those who are watching it from the very beginning, I will appreciate they are basically actively participating in listening and as well as to commenting and asking me a very interesting question. So thanks for watching. See you in the next class.